Hello and welcome back to Mechanochemistry Discussions. This seminar series is hosted by NSF-funded Center for Mechanochemical Controlled Chemistry, or CMCC. My name is Mateusz Marianski. I'm one of the center's investigators. As always, the goal of this seminar series is to bring our community together. The seminar streams live on the third Thursday of every month at 11 a.m. Eastern, and they're also available to watch anytime on the YouTube channel. Also on YouTube, you will find all previous speakers that participated in this seminar series, and I really encourage you to check them out. We also have some excellent speakers planned for the following months, and we hope that you will also join us for them. Before we get started, a few quick thank yous. First of all, Dr. James Batias, the Center's Director, Jennifer Belzik, the Center's Administrative Coordinator, Frankie Antilon, our Outreach Coordinator, and two CMCC students without whom the seminar would not happen, Ryan Kwok and Brer Hilsabek. Please do continue to follow us on YouTube channel at CMCC Discussions, at CMCC Mechanochemistry Discussions. And before we start, a few quick guidelines. This webinar is being recorded. If you have any questions during the webinar, you can either email them to us at cmccdiscussions@gmail.com, or you can post them directly into the YouTube channel. Either way, they will be propagated to the speaker at the end of the seminar. We also encourage you to provide a feedback through this survey that we created, and you can scan the QR code and please let us know what we can do better. Without further ado, let me introduce today's speaker, Professor Guido Kickelbick, a professor of inorganic chemistry at Saarland University in Germany. He studied chemistry at the University of Würzburg, where he also earned his PhD under the supervision of Ulrich Schubert, and his research focused on soldier-derived surface-modified metallo-oxo-clusters. After completing his doctorate in 1997, he received an Erwin Schrödinger postdoctoral fellowship and joined Krzysztof Matiaszewski's group at Carnegie Mellon University in the US to research controlled radical polymerization for the design of hybrid materials. After returning to Vienna University of Technology in 1998, he completed his habilitation and was appointed associate professor in 2003. In 2009, he was appointed to his current position at Saarland University. His research focuses on hybrid materials, nanocomposites, and surface functionalized nanoparticles, with his most recent activities expanding into mechanochemistry for the synthesis and activation of inorganic materials. He is the author of more than 300 publications, has written a textbook, edited several books, and served as Dean of the Faculty of Science and Technology at Saarland University from 2016 to 2020. It's my pleasure to welcome Professor Kickelbick to Mechanochemistry Discussions.
So, hello everybody. My name is Guido Kickelbick. I'm from Saarland University. I welcome you to my talk on expanding the reactivity of metal oxides through mechanochemical activation. I'm located in Germany at Saarbrücken. This is a town next to the French border in the far west of Germany. And we are not exclusively working on mechanochemistry. Our fields, our research areas are in the fields of hybrid materials, nanocomposites, nanoparticles, and specific materials for specific applications. And we ran into this field 12 years ago when we were trying to make nanoparticles with mechanochemistry. So for us, doing more or less solids, what are the advantages of mechanochemistry and what are the effects of mechanochemistry? And I just want to show you some. So if we look at the mechanochemical treatment of a crystalline metal oxide, of course, what we can see is a crystallite size reduction, and then microstrain in the lattice. This usually increases a lot. Additionally, we see for the formation of defects, we see phase changes, an amorphization of the products. And if you look around in all of these different aspects, at the end, what's happening is you have a change in the chemical reactivity. So maybe it's a little bit different from typical organic mechanochemical reactions, but for us, these are intriguing effects on the mechanochemistry of materials and especially on the change in the chemical properties of solid state materials. One of the major points, one of the major techniques we are using for getting out information on the different, let's say, property changes is powder X-ray diffraction, and especially here, Rietveld refinement. And I just want to give you a short overview how this method can help you. So generally, you see here that inorganic solids are usually characterized by powder X-ray diffraction. And during milling, here you see one specific example. You start with a pristine material, and what you definitely see is that the reflexes get broadened. So the patterns are broadened, and in this broadening, you have two different effects from the crystallite side, and one is the crystallite size, and the other one is the strain. And these are very important aspects concerning the further reactivity of the materials. And on the right-hand side, you see, for example, that even after short times of milling, you get dramatic decrease in the size of the crystallites, and at the same time, and this is what I don't show on this slide, but what I just want to tell you, at the same time, you get a huge increase in the strain in the materials. So what can we detect with this method? We can detect the product formation, we can detect phase changes, we can detect crystallite size reduction, amorphization, analysis of the microstructure, and in the future, we want to also try to take advantage of the temperature-dependent reconfiguration after milling to get an information of the, let's say, kind of amorphization and the kind of defects we are forming in these solids. This is just a short overview. I will also present you additional characterization methods during my talk. Okay, this is a short outlook of the different topics I will show you today. One is phase changes during milling and the effect of surface functionalization on such phase changes. Then I will focus on the mechanochemical reduction of metal oxides with alkali metal hydrides and on the mechanochemical activation of metal oxides for alkali metal intercalation. So we start our journey a long time ago. When I was beginning with this type of chemistry, I was asking myself, okay, if I put a solid metal oxide in a mill, what happens with the solid? And can we use the solid as a probe of the energy input in the mill? And if you think about that, this should be possible because phase changes are usually implemented if you change an outside parameter like the temperature. And our question we had at that time was, do phase changes also occur in the mill? Of course, then you have to find a sample system, a probe, which helps you in detecting these phase changes. And the phase changes should be, of course, in a window where the mill can access the energy you need for the phase change. And here is a very simple experiment we did in the beginning. So we used titania at that time, also for nanoparticle synthesis. And we have 3 different phases, usual phases in the titania phase diagram: anatase, rutile, and bruchide. And sometimes at higher pressures, you also can get high pressure phases. This is mentioned here in this phase diagram with titanium 2, O2 2-phase. This is a high pressure phase. But generally, we were only thinking about these 3 different phases. And the low temperature phase is the anatase phase, and the high temperature phase is the rutile phase. So the hypothesis is, in the mill, if you put their anatase in the mill, you get a phase change to rutile. Let's check whether this happens. So we did several experiments. The first one was just putting the pure titania as anatase phase in the mill. And our expectation was that we see probably anatase, the amount of anatase decreasing and the amount of rutile increasing. And probably we will reach also a high pressure titania phase. And then we did another experiment. We put in phosphonates, and we were interested whether this phase behavior here changes in the presence of these phosphonates. So let's have a look on the different phases. So what you see here is the phase composition in weight %, and you see different milling times and different speeds of the high energy ball mills. So we start here, for example, with 200 RPM, 6 hours, 200 RPM. And in the beginning, you see this is our pristine materials, 200 RPM. After 12 hours, you see that the anatase phase changed partially to a high pressure titania phase. And in black, you see the rutile phase. This is what we were expecting. So the higher the energy input and the longer you mill the system, you generate more and more rutile phase. So at 48 hours, 300 RPM, more or less all of your pure anatase phase was transferred into the rutile phase. This was our expectation. But if you put in now phosphonates, we saw dramatic changes in this behavior. So we also saw that the anatase phase was decreasing, but what we couldn't detect was a large increase in the rutile phase, but an increase in the high pressure phase. And usually you have to know that these high pressure phases are metastable. This means that they are, after some time, getting back into the rutile or the anatase phase. But if you do this same reaction now in the presence of the phosphonates, these high pressure phase becomes stable over time. And this is something very interesting, because in the mill, you can stabilize by a small additive high pressure phases, which you usually can only stabilize or which you only can detect under really high pressure experiments. Another thing we were detecting is that you probably know that titania is a white pigment. And if you mill that in the presence of phosphonates, you see that over time it turns grayish. Yeah. So the question was, where does this color come from? So we did this experiment in a zirconia jar. So we didn't do it in a tungsten carbide jar, where you probably have some problems with aberration and therefore you get impurities in. In our case here, what we were detecting is that we reduce a part of the titania 4 to the titania 3 in presence of these phosphonates. And we could detect that by EPR spectroscopy, which tells us that titania 3 is present. And this is a very important, this was a very important experiment for us because we saw that reduction of highly oxidized transition metal oxides is possible in the mill. So generally, in this old study, we saw crystallite size reduction. We can stabilize thermodynamic favorable phases during milling, like you have seen in the left example, the rutile phase. But we can get other phases stabilized if we add an additive. Okay. Good. So this was the first example. And now we enter into a second point, and this is the reduction of metal oxides with alkali metal hydrides. So when we started with that, the question was, can we do a reduction in a mill? So usually you do reductions of transition metal oxides in a hydrogen stream at high temperatures or in the presence of a hydride, and you decompose the hydride at high temperatures. And here you see some results from the literature. So you can really reduce these transition metal oxides in the presence of hydrides. So the good thing is if you use alkali metal or earth alkali metal hydride, this is a solid. And this means that it should be possible that you also can do that in a mill. So what were our expectations? What can happen in a mill if you place there a metal oxide and an alkali or earth alkaline hydride? So you can reduce it to a reduced species. You can to a fully reduced species. You can reduce it to a partial reduced species. You probably get alkali metal incorporation, especially if you have these small alkaline metal hydrides. You can probably get a reduction to the element or an alkali metal incorporation and a reduction. So these were the possibilities, and let's see what's happening in the case of titania. So we again took titania. Yeah, titania is very interesting. We are also doing a lot of applied projects. So titania in its anatase form, you probably know that this has a high photocatalytic activity. Rutile has nearly no photocatalytic activity, but it's used for UV protection. And therefore, our interest was whether we can reduce these systems, because it was known from literature that you can generate black titania. So titania usually is a white pigment. And now what you can do is, under reductive conditions, you can generate black titania. And in black titania, you either have a full or a partial reduction of the titania 3, the titania 4 to the titania 3. You can do that by traditional methods, and it was already done also in the mill. For example, reduction with pure sodium, reduction with lithium, or reduction with these titanium hydrides, and you end up here with black titanium. Okay, so but our question was, can we also do that with usual alkaline hydrides? And as you can see, this is possible. Here you see two different reductive species. One is lithium hydride and the other one is sodium hydride. And remember that we start with a white color, and what you see here is that you get a grayish color in the case of sodium hydride, and you get a nearly black color in the case of titanium hydride, depending on the milling time and the ratio of the reductive species. In these experiments, we start always with rutile, not with anatase, because this was at that time the only titania we had in our lab. And what we also regularly do is we detect the pressure increase in the milling yars. Yeah. So what you can see is that over milling time, you always have here, in both cases, you have a pressure increase. And this pressure increase is most likely coming from the release of hydrogen. Yeah? We could test that after the experiments with a simple test. You know that you have a small test for hydrogen, and we could prove that hydrogen was in the milling yars. Okay, so we could prove something changed here. The question was, did we really do the reduction? And as you have seen in the previous slides, is that EPR spectroscopy can help us here. So with EPR spectroscopy, you can detect unpaired electrons, and in the case of titanium-3, you definitely have unpaired electrons. So what you can see in this spectra is lithium hydride as well. After 10 minutes and 60 minutes was forming these quite high concentrations of titanium-3. But sodium hydride, even after 60 minutes, didn't deliver any signal. So there, the reduction potential was much lower. And this is a little bit counterintuitive concerning the chemistry of the hydrides. I put you the general knowledge about in comparison of lithium and sodium hydride on the right-hand side. So lithium is has a smaller iron, has a higher lattice energy, has the more tightly bound hydride, and therefore is the less reactive hydride. Yeah. However, in our experiments, we saw that lithium hydride has a higher potential to reduce titanium. So the question was now, why this is the case? And we figured that out by Rietveld refinement. So what we have seen there, or what we have detected there, is the following, that lithium is intercalating into the titanium lattice. This means that you generate lithium titanate, most likely only in the surface. Yeah, but we definitely can prove that lithium titanate is present there. So, and now you can think of why we had these changes in the reactivity here. Because this is known from battery business. If you do a reduction and an intercalation, this sometimes helps you in the reduction. So you have two effects then, the intercalation and the reduction. And if you do both, you can see the reduction. If you can do only one, sometimes the reduction fails. And why is now lithium better intercalated? This is clear because it has the smaller anion, yeah, cation, sorry. This is a smaller cation, yeah. And we could prove that by different methods, not only by the Rietveld refinement, but also by ICP-MS, that lithium was intercalated in this reaction. Another method we often use here is solid state NMR. What does this tell us? So if you look for the 6 lithium solid state NMR, you could prove that a broadening of the peaks in the lithium NMR gives you usually an information of the environment of the lithium in the lattice. And you can deconvolute the experimental signals, and then you can see that you have a major peak for the usual environment, but this is quite broad already. So this tells you something about amorphization, or that not all lithium sites are occupied. Yeah. And in addition, what we see here is this small peak here in the deconvolution, and this is the interaction with titanium 3+. So this gives us some additional information about the species which are formed. In addition, what you also can do in the solid is look into the Raman spectroscopy, because there usually mechanochemical treatment gives you broader peaks and sometimes also peak shifts. And this tells you also something about the structural disorder. And here you see that clearly in the case of sodium hydride, you have really nearly none of such shifts. But in the case of lithium hydride, you see that there is a large shift in this region. Okay. So I told you that I think there's something went wrong here.
Guido,
Sorry to interrupt. I think we lost the slides. Yeah.
Yeah. Wrong. Sorry for that. Okay. Okay. Sorry for this. Yeah, you should see the slides again. Of course, you have seen that we generated black titanium. Yeah. And so if we generate black titanium, you should see that in the absorption spectra. And the absorption spectra also help you in detecting the band gap. Yeah. You can do here an analysis. It's called Kubelka-Munk analysis. So you look at a specific absorption band, and then you, let's say, take a linear regression of your signal, and then you can tell something about the band gap in your material. And what you see is that you have a band gap shift to a lower energy, and this is due to the reduction to the titanium, to the black titanium. Yeah. Okay. So the final question was now whether we can do photocatalysis with that. I told you that rutile is not photocatalytic active in the beginning, but if we reduce that, it should be possible. Yeah. So here you see a comparison. This is a standard test with methylene blue under two different wavelengths. One is in the UV region and one is in the cold white region. So 400 to 700 nanometer and 365 nanometer. The standard reference is P25. This is an Anatas reference. And for the decomposition, and what you see here, the decomposition of methylene blue in the P25 case decreases very fast, or goes on very fast. In our case, the methylene blue with pure titania without any mechanochemical treatment is already not so bad, but it becomes better in the UV region for the mechanochemical treated systems. And in addition, also in the case of the visible light region. Okay, so the question was now, okay, can we do that also with other oxides? And here are some examples. You can look up the references here. I will not present you this magnesium vanadates today. I just want to give you a short glimpse on these vanadium oxides. So what we wanted to do here is not using lithium hydride, but sodium hydride together with vanadium oxides, vanadium 5 oxide. Yeah. And this is an experiment a bachelor student of me was doing during his bachelor's thesis. And this was really strange. What was happening there, and now it's strange that it doesn't start. So let's see whether we can do that in another way. Yes. So this is a mixture of vanadium 5 oxide and sodium hydride in a glove box under argon. And the student treated that just by mortar and a pistol. So it's under argon atmosphere. And you see that this is a very rigorous reaction. Yeah. So the question was, how can this happen? Yeah. So you have really a highly exothermic reaction in this reduction. And you can also follow this by using, again, this special equipment, pressure equipment and temperature equipment. And what we could see is that the onset of the reaction occurs already after a few seconds, depending on the concentration of the sodium hydride. Yeah. And again, we could confirm that hydrogen gas was formed in the yar. Yeah. Okay. Good. So here you see again that we get a formation of a new product depending on the equivalence of sodium hydride and depending also on the milling time. Yeah. Generally, the hydride concentration is more influential than the milling time for the final sample composition. And the question was now what it was developing during this reaction. And this you can solve with Rietveld refinement. So what you see here are the different amounts of the hydrides. Yeah. So from 1 equivalent to 4 equivalents. And what you see is at the beginning, you have a strange composition of different oxides and reduced oxides. And at the end, you form only 2 different sodium vanadates. Yeah. So it seems that you have here a very similar effect. You have a reduction of the vanadium, and in addition, you form an intercalation of the sodium. The question was now, why is this reaction so exothermic? And you can follow this reaction also by calculations. So you can write on a piece of paper the probably occurring reactions with the sodium hydride, and then you do a calculation with on a DFT basis. Yeah. And what you figure out then is that the formation of sodium hydride, sodium vanadates with the oxidation state 5+ is the most exothermic reaction. So this seems to be the driving force of this reaction. Yeah. And the use of more sodium hydrides, you get in the use of more sodium hydride, you get more exothermic reactions, and both results are really in a very good agreement with the experiment. So what we do currently with the reduction is we first do the calculations and we then do the reactions in the reaction yard. Yeah, we of course tried also different other reductive agents here, for example, lithium borohydride or sodium borohydride. But if you do that with these reductive compounds, you always get not the same results as with sodium hydride or lithium hydride, because we think boron oxide is forming. We could prove that by boron solid state NMR. And this is a side product, and this, of course, reduces the mechanochemical impact in the reaction. Yeah, so it's better to use the hydrides instead of using the borohydrides. Okay, last point. I just want to show you that this lithium metal oxide formation is also interesting for applications. And here you see the formation of lithium titanate in the ball mill from lithium hydroxide and titania. Again, we proved by solid state NMR that in this case, not only the usual voids are addressed by the lithium, which you would expect under high temperature conditions, but also other voids are also addressed, like the tetrahedral voids in the lattice. And this leads then to higher lithium conductivities. So here you see two examples. These lithium conductivities were measured by impedance spectroscopy. In black, you see the pristine material, and in green and red, you see the high energy ball milled materials. And what you can detect is that you have an increase of the lithium conductivity compared to the pristine materials by several magnitudes. And in addition, what's very interesting is that long milling does not always help. Yeah, so at short milling types, the increase of lithium conductivity is much higher than with longer milling types. Yeah, this is a very interesting aspect, and we see that in many different reactions that longer milling times not always help you. So here is another interesting experiment. We wanted to generate here manganese oxide, this manganese oxide with the oxidation states 2 and 3. And this usually needs really under usual conditions, so temperature-like conditions, it takes you a long time and usually needs to be done under very restrictive conditions concerning the oxygen presence. But in the mill, you just mix manganese 2 and manganese 3, and you get out the final material. After 3 hours, you start to see it, and after 12 hours, the reaction is over. Yeah, okay. But the question now again is, in the beginning, I told you that chemical reactivity should change. So the question is, how can we prove that chemical reactivity on solid changes? And one potential proof you have seen already before is lithium intercalation. So the question is, if you do an experiment without electrochemical intercalation, just by doing intercalation by a chemical approach, you have butyllithium and you take the manganese oxide and you put it in a suspension with N-butyllithium in hexane under reflux. Do we see a difference between the high temperature material which you get usually under usual solid state conditions, or the material which you get from the mill. And here you see already the result. If you have the usual material, the coarse-grained materials, you need several days to lithiate that. With the material in the mill, you get after 1 hour 50% lithium intercalation, which is a very interesting result for potential battery applications. And we again could prove that this activation, as I have shown you already in one of the first slides, can be done after 10 minutes. This is nearly long enough to do this activation. And then if you mill longer, this seems not to have a similar effect. And we think there are two reasons for that. One is that you have this crystallite size reduction, and the crystallite size reduction leads to shorter waves for shorter distances for lithium intercalation. And the other reason is that you have also amorphization, a formation of more defects, which probably help during lithium intercalation. And again, this is a very similar result. We published that last year. This is just to show you again that long milling times not always improve the results, but after short milling times, you always get, in most of the examples already, very nice results during this chemical activation of mechanochemical activation of the manganese oxide. And again, we could prove by impedance spectroscopy that we have better ionic conductivities in these cases. Okay, and with that, I want to conclude. So you have seen that simple mechanochemical reduction of metal oxides with alkali metal hydrides is possible. I have shown you that the reduction of vanidates or the production of vanidates by mixing vanadium oxides and sodium hydride in the mill is a very easy way to do this intercalation and at the same time the reduction. And in the last point, I have shown you that activation of manganese oxides can increase the lithium intercalation, which is a potential way to get better, more activated battery materials. And with that, I like to acknowledge my group. Of course, the work was not done by me, but mainly by Anna Michaeli, Tobias Straub, and Andreas Gieselmann, together with Oliver Janka. And we have several cooperations in this project. I also like to thank the German Science Foundation, Alexander von Humboldt Foundation, and several other money providers. And I like to thank you for your attention. Thanks a lot.
Thank you very much, Professor Kickelbick, for your talk. We have a couple of questions from the audience, so if you could answer them, it would be great. So the first question is that at the beginning of your talk, you briefly mentioned abrasions.
Yeah.
And during the grinding of the titanium oxide. Could you comment about what's your opinion about the importance of the particle size versus abrasions that are being formed during the grinding for the further reactivity of the oxides?
Yes, we did some studies in the beginning of our work on that. So usually what we do is we use ICP-MS to get an analysis of the final products. And what we could show in our first studies was that, of course, it's always, you always treat, let's say, mechanochemical activation crystal size reduction, also with abrasion. So the impact, of course, is not always the most important thing. Yeah. And I guess you, some of you know that. I mean, you can do a lot of mechanochemical reactions in PMMA YARs, yeah, where you don't have a huge impact. Yeah. But what I can tell you is, so at the beginning, we were, I think, doing what everybody would do. We were thinking taking the tungsten carbide system, which is the hardest one, would help us the most in doing the let's say the mechanochemical activation and the mechanochemical treatment. But what we have seen is that then we run into an abrasion problem. Yeah, therefore we went to softer materials, so silicon carbide, silicon nitride, or zirconia to get less abrasion, and we figured out that we received very similar products. So after that, we used not so hard materials anymore.
Mm-hmm. Okay, thank you very much. So the second question is that in the second part of your talk, you showed a little bit of the DFT calculations. Do you have similar calculations that will corroborate your findings of the incorporation of the sodium and lithium cations in the titanium oxide lattices? The argument that you're making about the easiness of incorporating the lithium cations there.
At that time, we didn't do any DFT calculations, so we have to redo that. Yeah, but I think you will find a similar dependency. So I think in these cases, because the lithium is so small, you probably see that the lithium intercalation helps you in the reduction process. Yeah, so you are absolutely right. We would need to redo these calculations to check whether there we can also predict the formation of this lithium titanate.
And we have one more question, which is that on the vanadium oxide plus sodium hydride system, you got the flash in the glove box when grinding with mortar and pestle. And then you ascribe the exothermic reaction to vanadium oxide reacting with sodium oxide. That's what you got on the number reactions on the slides. And so what happens if you just do the number reactions with the mortar and pestle in gloves box under argon? And is there hydrogen gas evolution? Is there hydrogen gas evolution causing the flash?
But this was under argon.
This glove box was under
this
argon.
This was in the glove box under argon. Yeah. So yeah. So what you have seen is not. I don't think that this is the ignition of hydrogen. It's just the exothermy of the reaction. It's not that something ignited there. Yeah. So gas. It's the exothermy of the reaction itself. I don't think that there will be a reaction between argon and the components. Yeah.
Okay. Thank you very much for the clarification. So yeah, these are all the questions that we have. So once again, thank you very much for the interesting talk, and thank you very much for accepting the invitation to give the talk as a part of the seminar series. And it was a pleasure. Thank you.
Thank you.
Thank you, Professor Kickelbick, for the outstanding presentation, and thank you very much all the viewers for joining us. Just to remind you, we have all our previous seminar speakers available on YouTube channel to watch anytime, and I really encourage you to check them out. Also, we would really appreciate if you can provide us the feedback through this survey. You can scan the QR code or find the link in the description. This will really help us to understand what we can do better about our seminar series. And finally, I would like to remind you that we have some great seminar speakers planned in the upcoming months, and I really hope that you'll join us for all of them. Thank you very much again, and see you next time.